Welcome back. Today we'll learn classification and I hope you recollect the definition of regression, that whenever we have the output variable, that is a categorical variable, as a numeric, whether integer or the float or double kind of variable, that was a regression kind of problem. In classification, the response variable is category, basically nominal, most of the time nominal only. Although ordinal can also be used as a classification, but as per my experience, I have seen most of times nominal only, and ordinal generally taken care in regression. So what are the various types of the classification problem? Like you have the very distinct type of the outcome. For example, if you are trying to predict a gender, say it could be male, female, or color, red, blue, green, and so on. Let me show you the example which will be working. Throughout our classification, we'll be working with iris data, and iris is one of the research data that have been published long time back. It is a type of the flower, so that has the 4 different independent features, and based on that outcome of the flower is there. So let us see what are the different types of flower. So there are 3 different types of flower has been over here. So Setosa, versicolor, virginica, and these 3. So we'll work on the reclassification problem where we'll try to predict the type of the flower given the various independent attribute. So this will be our classification problem. Let us proceed. Yes, that's nice. So what are the classification problem we have just discussed? Wherever we have response variable and we of the nominal nature and we want to predict that. This is generally happens wherever we have the distinct outcome to predict, and distinct outcome not necessarily it could be only 2 outcome, it could be 2, 3, 4, 5, as many as possible. That is things. And I recollect these kind of things are already happening through a long time. And I have seen whatever literature I have seen, almost till 100 years ago, there used to be some concept called decision tree. So as if you recollect the way we wish to, with the way we have defined the tree part, I hope you can recollect this slide where we have given the brief overview how the tree structure really works. So here the outcome was, whenever the outcome become class, that becomes the classification problem. Yeah. So this tree classification is there for almost good number of years, and this is also sometimes known as a CART. CART means classification and regression tree. So CART means basically the very basic tree algorithm that is to use both for classification and regression. One of the very important point of the classification tree is always the tree pruning. Tree pruning is basically height of the tree. So if you recollect, height of the tree means basically depth. We should have the depth in such a optimized way so that it is neither underfit nor overfit. We'll discuss this in detail when we come to start discussing the algorithm. So this is a brief about the classification. Let's go ahead and learn the confusion matrix. Confusion matrix is one of the very old matrix that used to identify the accuracy of the classification problems. So let's start with the first very basic part of the confusion matrix. Generally, if you see, when you have a 2 outcome of the problem, say good and bad, actual we put it generally in the row and the predicted in a column. So if actual is good and predicted is also good, that is called true positive. If actual is bad and predicted is also bad, so it is called true negative. So these are the ideal scenario, and we often want to get into these 2 zone always. But world is not that much perfect. So definitely we do little bit of mistake sometime. So when actual is bad and we have predicted good, that is called false positive. And when actual is good and we have prediction is bad, so it is false negative. This is in statistics. This is also known as a type 1 and type 2 error. So false positive is a type 1 error and false negative is a type 2 error. This kind of questions always comes if both are a kind of error, which one to minimize? Which one to minimize? So if you see how can we minimize? Let me take this example in one of the. Let me take it here. Okay, here. If you see, how can we minimize? Let's try to see that if we are trying to minimize this. How can we minimize? We can minimize either pulling this part here. But if you recollect, as soon as we try to minimize this, we have increased this true positive. That's quite good. But at the same time, we have also increased the false positive. That is not good. It means while minimizing the one kind of error, we have maximized the other error. Similarly, let's go back here. Now, if you try to increase the try to decrease the false positive, we can do it in a few ways. Like if you try to reduce this, yes. If you recollect, yes, we are able to minimize the false positive. It maximized true positive, quite good. But at the same time, it has maximized the false positive, basically increase the false positive. So the bottom line is you cannot minimize both kind of error together. You cannot minimize both error together. What you can minimize and which one you can minimize depending upon the type of the problem you are trying to solve. Then what is the type of the problem? Let me give you the example. Let me take the one example is the traffic situation. Let's assume that you are standing on any traffic, and if you see that there are if few people break the traffic, okay, that's fine. They may get caught, they may not get caught. But the situation what it demands here, even though if you cannot catch few traffic violators, then do not catch even a single innocent. It means you don't catch the innocent people if you cannot catch the violator. So which kind of, if you catch the innocents, what kind of mistake you are trying to do? Just you can pause for a video and think over it. Here the situation is that catching innocent by the traffic police. So it means you are good, but you are getting predicted as a bad. It means this kind of situation it is there. You are a good, but you are predicting as a bad. It means this kind of situation. You are good. It means you are trying to do the type 2 error. Another example is, let's take the medical situation where patients are getting tested for some kind of disease or virus. You may be infected, you may not be infected. If the doctor take the judgment to not take the test, that is, but if you have the problem and if you're not taking it, then what it means? You have the problem, it means you are infected, but doctor is saying you don't need to take the test because you are good. It means you are committing this kind of error, false positive. So depending upon the situation, you see what kind of error you are committing and what you should do it. So in case of traffic situation, you should not catch the innocent people at all. In case of medical situation example I gave, if you have even the iota of doubt, definitely you should basically see that if that can be confirmed using the test or something, so that person, all the infected people should not be told as a good. It means they must be treated. That is what this situation is. So depending upon the situation or the problem you are trying to solve, you should see which kind of error you should minimize and why. Okay. Now, see, when you are working with a classification problem, you may get balanced data and imbalanced data. So what is the meaning of balanced data? Balanced data means the outcome. Say, let's assume that here you had outcome of say 0 and 4, let me show you the example. See, here the outcome is these 3. So if these 3 means if approximately all are having around 33%, that means that is quite good. But that is a balanced data. But if it is imbalance, means let's assume that for one is having 80%, another 10. It is coming towards imbalance. Sometimes it happens that okay, this setosa is 95%, 2% versicolor, 3% virginica. It means around this is imbalance problem. It means the balance basically distribution of all these output labels are not equal. If you get a balance problem, then this is the way you have to judge the accuracy of your problem. So here there is something called ROC AUC curve. ROC means receiver operating characteristic and AUC means area under the curve. So the thought process is to get the maximum area in this curve. Why? One thing, if you observe, this area, this curve is getting from on x-axis there is something called false positive rate. Y-axis true positive rate. When we can get maximum in this area, when this point is almost here. In that case, what will be the area? Under this curve, all the possible area will be there. But actually, practically, you will not get that kind of situations. You will always get this kind of curve. And here, a few of the statistics which you generate: true positive rate. True positive rate is TP, that is true positive, divided by true positive plus false negative. FPR here, false positive rate, false positive plus true negative. TPR is also called sensitivity. I'll explain just a while ago. Okay. The second thing is imbalanced. Imbalance means at least one or two of the label is having not the equal proportion. In that case, you go ahead with precision and recall. So P is precision and recall AUC. Here again the curve are getting drawn and the curve maximum area should be there. Precision talks about that how good your predictive power is. Recall means that that positive, it means if you have say 0 and 1, then what is all the positive one? It means 1 they have been predicted correctly. Recall is also known as a sensitivity, and same sensitivity, whatever the formula you see here, this is also formula same thing. So TPR and recall have the same thing, only two different names. So both are called sensitivity. And in case of, let's say you have the outcome 0 and 1, and 1 is, if you are trying to predict that 1 becomes your positive, so that one become your sensitivity. 0 become your TNR, or it is also known as specificity. So basically TNR. These are the two terms you will always see. You'll always see in the classification problem that trying to predict the accuracy of the classification problem. You may always see that it is having so many. It has so many terms. How should I recollect? Then the kappa statistics comes into the rescue. That instead of having so many things, if you want to observe say 1, then the kappa statistics works, and that is statistics again between 0 to 1. If 0 to 0.2, it means that okay, just okay. 0.2 to 0.4 fair, 0.4 to 0.6 moderate, and 0.6 to 0.8 substantially good. 0.8 and above is the basically perfect. So if you want to observe one kind of statistics, this works. Kappa is the one. But kappa does not work 100% of the time. In one or two situations, it does not work. I will explain you while explaining the hands-on. So this is the confusion matrix. I have seen that people do not understand in the first view. So do not hesitate to repeat this video again and again. Do not hesitate, or if you still have the question, do not hesitate to write your question in the discussion forum. We'll go ahead and do the practice for logistic regression. That is the one of the classification problem, performance matrix, which you confusion matrix we saw. Then we'll see the various things. One thing more, if you want to see that how the confusion matrix is, why it is called confusion matrix. Confusion matrix is one of the matrices that has the capability to confuse most of the people. See, this is the definition at Wikipedia. Plus on the right side, if you notice, right side here, the kind of matrices it has. Huge. So it's my advice that if you are learning confusion matrix for the first time, do not hesitate to review this video a few times. Plus also if you are trying to solve any classification problem for say next 2 to 3 months, please revisit the literature again over here on the Wikipedia or some other thing. Do not hesitate to basically say that you remember everything. Do not get into that mode, that kind of overconfidence, because this is one of this matrix looks very simple, but this is the highly confusing in the beginning. So do not go in overconfidence mode. And in the next one, we'll start some of the advanced algorithm for confusion matrix. See you in the next one. Thank you. Nice.